Okay, we're getting started. I had a little bit of discussion about the virus. This is for you, John, since you're not in the classroom. You are in a state, though, that already has confirmed cases. I just think it's a matter of time, and it's going to happen in Colorado within 24, 48 hours. That's kind of what I'm thinking. But at any rate,
As long as it doesn't affect finals.
well, they're saying it could affect the Olympics, right? In Tokyo.
They're not here, so
Yeah.
I care about here.
Yeah. Okay. Just to back up a little bit, this is what I put up last Thursday or Friday morning when I posted the video. We are going to do the exam a week from this Thursday, so I'm going to kind of walk through the roadmap the way I see it. I will have some form of review on Tuesday the 10th. I also plan on, because I'm going to be going over the Hilbert transform today, I'm going to do something rather than pushing new material really hard, but wanting to give you more chance to kind of force your hand to work existing problems to get ready for exam 1. I'm going to take problems from set number 5, because I notice I didn't put up solutions for everything. I only put up hints. So what I want you to do is note that there's 2 more problems I want you to turn in. They're just on the Hilbert transform, sort of a drill down. And that would be number 6, which is a drill problem. Just work through those problems. And then problem number 7, 273 A and C. We'll kind of look at some of that today probably, but I want you to turn those in too. So what you're going to do is rather than posting a new set right now, I will wait until what we finish up on next Tuesday. We'll be pressing onward, but I'm drawing the line on the Hilbert transform as I see it right now. So I'm just going to give you something more to do there. I obviously won't make any homework assignments due until after next week, except for these 2 problems for next Tuesday. So you're turning in problems now. Some of you are messing around. I know Colton was visiting me during office hours, so if you want a few more hours or something and just get it off your chest, that's fine. Actually, he turned his in, but then he went somewhere. I don't even know where he went to. I do plan on having a quiz on Thursday, though. It will cover double sideband, AM modulation, AM efficiency, all those kind of first 2 units in chapter 3. So double sideband and AM is what it will be. There's always 2 parts on a quiz, so one of them will be just double sideband, maybe transmitter, something along that line. And then the other one will be amplitude modulation. Could be efficiency, modulation index, any of the types of problems that are up here. And in order to prepare for that, what I'll plan on doing is putting up set number 5 solutions all the way through number 5, because that covers the problems I'm saying the quiz will be over. And then problems 6 and 7 off of this sheet, which are the Hilbert transform, the ones I'm going to have you turn in next Tuesday, I won't post those. I'll just add to that later. I'll use the thing that Colton asked me to do, and that is when I put the solutions up in the next day or so. Hopefully I can do it. I'm not sure what hour I'm going to do it in, but I will just keep accumulating more. And then after the homework, problems number 6 and 7 from this sheet get turned in on Tuesday, then I'll just add those solutions in too, so that it'll just be cumulative all the way along without me pushing out a set number 6 until after. I might decide to push a set number 6 out there on Tuesday or something, but it won't be relevant for anything that you're doing next week. It will be for after. And then the first project is going to come out too. It's going to be ready to roll out after the exam. So I'll start talking about it as early as Tuesday if I feel so inclined to want to talk about it, because it's related to single sideband.
Are you going to be individual or partners? Or you haven't decided yet?
You can be partners. We have one graduate student, so he has to work alone, which is fine, I think, right?
Yeah.
You'd like working alone, I'm guessing. Maybe, maybe not.
Yeah.
I'll let you have partners too. So what does that mean with the current configuration? That means it's 2 twos, right? Because I think we dropped somebody in the class, right? Did he officially tell you?
Yep.
Okay. I can see the writing on the wall. Honestly speaking, I've been doing this too many years. There's just signs. I won't tell you what the signs are because it's just sort of something that you just have this feeling. It just comes from practice, I guess.
Who's next, Dr.
You want me to? Do you want me to give you my predictions? I don't know. I'm not going to try to do that right now.
Oh no, I can't afford to drop a class. I gotta
Yeah.
pass them all.
Okay.
All the way.
And John, you're a graduate student, so you'll be working alone on the project, but you knew that already anyway. Just doesn't work when you're too far away to work with a partner, but he's not eligible anyway. So that's the roadmap. So that, like I said, there will be the quiz, and I'll get these solutions up through number 5. And I think the 2 problems that you've turned in now are kind of interesting. Number 311, the one that you turned in, that is a type of problem that could be on a quiz or on an exam problem. That's prime material. The first problem, 265, that had the numerical stuff in it, that's not really exam type material. That's take home and mess around with it on the computer and be satisfied that you can do some plots and get some visualization about what's going on. I like the problem a lot, though. It's a little bit too involved for an exam problem. And yeah, the other thing I'll do is I'm going to be putting up 2 old exams, so I'll get that going here too. So you'll have 2 old exams that will be down below here where I currently have my TBDs in here. So I'll give you 2018 and 2019. That's my tradition, to just roll back 2 years, and so you get to see what those are. And then I have to use the rest of my resources to create the exam or write new problems. Whatever seems like the right thing to do. I'll take ideas, though. I mean, we'll talk about that on the review, when I kind of review what we're covering for sure next Tuesday. So I was looking at Hilbert transform. We want to back up a little bit. Actually, what I want to do is I want to go back to the simulation that we never finished going through to make sure I can get through that. And then there's some more problems on AM efficiency. So these types of calculations right here, I'm going to look at a little bit more with that. And this is candidate material for the quiz, most certainly, because it's kind of the bread and butter of this area of the book. And amplitude modulation seems, in my mind, kind of old and not all that contemporary, but like I said, it's still used in legacy systems, and it gets you into the core of modulation theory. What are things that are of interest? When we study FM modulation, what are the things of interest? I mean, one of the things we're going to see when we get up to the next chapter is FM avoids some of the issues that you have with AM, but it typically consumes a whole lot more bandwidth. So, and bandwidth, I tried to emphasize quite a while ago, is a precious natural resource. We only have so much of it, but if you need it, you get it. And right now, some modulations have more bandwidth allocated to them than others. Traditionally, though, the lousiest quality services are the ones that are packed in the tightest bandwidth, like amplitude modulation for broadcast, amplitude modulation for aircraft to tower, Single sideband modulation used for ship to ship and ship to shore, I think. It still uses that as a legacy scheme. Two-way radio, as in VHF that we'll talk about when we talk about FM, uses narrowband FM, and that's very bandwidth efficient. And that's the legacy behind that was police and fire. Does anybody in here ever have a police scanner, a scanner radio that they ever used in their life? No?
Maybe once upon a time.
Okay. Never excited you? I was excited about it because my father always monitored stuff. I mean, he was always listening to the police and the ambulances and all that stuff. And I grew up in a small town, so when things were happening, it was kind of like, it was pretty significant. I mean, it wasn't like Colorado Springs, a big city where there's lots of officers rolling around. And nowadays they have trunked radio and other scrambling means, so a police scanner doesn't necessarily let you listen to very much anymore. You can't, they don't really want the general public listening in. And back then you could do things that you weren't supposed to do. You could listen to cordless phones. You can still do that in some instances, probably the really inexpensive ones. Did anybody know that?
No.
I remember being in an apartment complex with my scanner, and I just, basically you could hear phone calls. It wasn't something that you wanted to do. It was just like, there they are, they're right there. They're not protected at all. So it makes you think though, especially if somebody's in an argument or something. Could be a bad thing.
So AM radio, so when's the first AM radio came out? When they first had those vacuum tubes, is that right?
Yeah, back around the turn of the previous century. I mean, in the teens, I think, in the single digits in the teens of 1900s.
To make an, I guess, AM radio without those vacuum tubes, right?
No, actually, the very first receiver and the simplest one, kind of alluded to in the lab, without using the super diode though, is a simple envelope detector with a crystal germanium diode, crystal diode or germanium diode, and a tuned radio frequency circuit, an LC tank circuit that had a variable capacitor on it typically, and you would get it to resonate, and then you would get enough voltage across that tank circuit that you would be able to rectify it with the diode, and there'd be a capacitor on the other side of it, and you could put a little crystal earphone on, very high impedance, didn't take much power, and that you could listen to AM radio. And you can still buy those as hobby kits. I mean, Radio Shack used to sell them. Hobby Lobby might sell something like that. Pardon me?
They're on Amazon. You can go.
Yeah.
Even for my kids, I bought them snap circuits,
Okay.
which they have an AM radio.
Okay. Yeah, that's right.
So,
I forgot about snap circuits. I ran into them when I was down at that restaurant on North Tejon that has the toy store and game store next to it. What's the name of that place? It's a classic Colorado Springs restaurant. But they had snap circuits in there.
I'm more interested in the game store you're talking about than the rest.
They sell, well, it's games. I mean, it's board games and card games, and it's all the.
Gamers Haven?
No?
Talking about Poor Richards?
Yeah, Poor Richards. There's 3 stores in a row there, right? They're all owned by the same family or something.
Yeah, the game store shut down though.
They did?
Yeah.
Oh, shit.
This
town's going to crap.
Games and hobbies.
Yeah, it does. Right? That hobby stop or whatever, over by the jewelry store, they went out of business.
Oh, it's those things. Okay.
At any rate, there are things that might have been in your past, but if you didn't do them, I guess it's your loss. You know, you can still relive that. They don't work very well in a building that has metal studs, but if you go into your house with wood studs, stay away from a plasma TV. My house, I have a plasma TV, which radiates a lot of RFI, radio frequency interference. It works really well with a very simple device like that. So what I want to do is just go back to the Jupyter notebook we were looking at. someday you were talking to me about Pi Audio, so one of the things, I'm not going to demo that in here. I could run it. I was running it last week, but with Pi Audio you can run things in real time and you can have slider controls. So this I was running and my system rebooted, so I guess I'd have to restart this again. But with Pi Audio you can actually do real-time processing, and one of the CommLab experiments has you use this, looping it along with the hardware and the RF board. I don't think it's in lab 3. It might be in lab 4 or lab 5. I'm not sure. Those of you that are in the lab, have you seen one where Pi Audio pops up? Because I don't remember which one has it in it.
No, I've pretty much saved the Python stuff for last.
Okay. It's going to be a data communications thing. You're going to send out a bit stream, and then you're going to flow it back into Pi Audio from your circuitry, and then it will get error detected in the Jupyter Notebook. They'll do the bit error detection in there to see if there are bit errors or not, using a PN code, kind of like in a real datacom scenario. Transmit, and then receive, and then feed it back in and do the data bit detection in the Jupyter Lab. But going back over to chapter 3, kind of where I left off with double sideband, the last thing we did is I changed the carrier frequency to make it non-coherent at the receiver, and we listened to that. So let's see if it's in the same state as it was.
Should we start your kernel?
On this notebook, probably not. I'll just make sure. Well, for 2 days in a row, this system, which sits in my docking station, rebooted because it had this need, according to Windows, right, to go refresh itself. That loaded my file. So, but this is a WAV file, so this was saved after I ran this. No, but I have to define some more stuff that's at the top. That's right. So I have to define that. I am going to want to do some digital, so I'm going to get a digital source in here, which required T-span, which I didn't do that one. So now I'm just going to drop down and verify that this was still here. Nope. D is not defined. D was defined where? I might have deleted something though. It probably was YD. Nope. Well, let me just go up to the top and start from the beginning, and then I'll get this figured out. What I wanted to do though was repeat the experiment with digital data. So what I'm going to do is I'm going to T-span. I'm going to uncomment that, and then I'm going to comment out the speech file, and I'm going to comment out the single tone file. So this is a pseudo-random sequence. Actually, it's random bits. So non-return to 0 bits is what I've got coming out here. And if I was to go look at them, you just see that they're plus and minus ones. So if I was to go do that, just look at a few of the bits. So non-return to 0, and we'll be learning about that later in the semester. Bits of so many seconds long or so many samples long, and this is just a bunch of the random bits in the bit stream. I'm used a random number generator here. So it's not periodic like the PN code would be. It has a very long period. So those get modulated onto the carrier. I mean, at baseband, they look like a sync function because we've been through that already. And then it's getting band limited because I'm using an upsampler and I'm trying to band limit it. So that's what that looks like. And that's what they sound like. It just sounds like it almost sounds like noise, which is what pseudorandom PN is, pseudorandom noise, right? That's what PN stands for, pseudorandom noise. So now I'm going to modulate that on 2400 or 24 kilohertz. So there's the spectrum. Just looking at a short time segment, you don't really see a whole lot in here because I'm limiting everything with that statement right there. I guess that doesn't remove it either. But where there's the modulation is called binary phase shift keying, but the way we're doing this with double sideband, we're multiplying a +1 bit times the carrier, and then when the bit flips to a -1, we multiply it by the negative sign. So effectively, it's called binary phase shift keying because when it's multiplying by a +1 bit, it's at 0 degrees carrier phase. And then when we multiply by -1, we rotate the phase by 180. So the carrier phase is jumping between 0 and 180 as each new bit comes along if it changes polarity. So there's the spectrum up on the carrier. And if I coherently demodulate it, take this back to 24,000, that happens to be a bit transition right here where it changed polarity. We've got some ringing due to the filter's frequency response, ringing in the time domain. But then it's down converted back to baseband. There's the double frequency term over here. And then I send it through the low-pass filter. And the bits are back again. There's ringing on the edges just because of the filters that I used aren't giving symmetrical ringing. I'm using filters that have a group delay problem, actually. So you've got that asymmetrical distortion. But there's the spectrum of the bit stream, and it's 1 kilobit per second. The reason why I know that is the first null in this sync function spectrum is at 1 over the bit period, right, from the PN code. Remember that discussion? But it's random, so it's not a line spectra, it's continuous. So I should be plotting YD. I'm just making sure. Yeah, it's YD, so it's got messed up, but this should make it correct. And that's just the bits. I mean, it just sounds like noise. But now what I want to do is let you see what happens if I do like I did before, make it not coherent. So I'll make it 200 hertz high from the way it should be. And when I go to low-pass filter the spectrum, actually I should make it very, very slow. Make it just be 50 hertz, I think, would probably be good. And then go down here. And those are supposed to be, it's supposed to be a bit pattern. The spectrum still looks fairly decent in terms of being a sync function, but those don't look like nice +1s and -1 bits. They look kind of all scrambled up. And that's the nature of not having a coherent carrier. If I was to go listen to it, it's not going to be, it sounds rougher sounding, but it's not really that I can discern the bits with my ear. It's just that if I try to take these bits and send them through a comparator to make hard decisions on them, you know, anything above a 0 I'm going to call a 1, anything below a 0 I'm going to call a 0, and then feed that into some data consuming sync, it's not going to work. It's going to be, the bits are going to be all messed up. They're not going to be what I think. There's going to be errors all over the place. So in digital comm, we have to have the coherent carrier. In the audio, remember, not so. And just to emphasize that, I'll kind of repeat this again. Get back to the right spot here. Those were the bits, but what I'm going to do is I'm going to put the speech file back in again, comment out, comment out the PN code. So now we have the speech back again.
Take the winding path to reach the lake.
And now I'm going to leave it. I'm going to modulate it up onto the carrier. And I'm going to demodulate it with just a 50 hertz error this time. And then recover it back to baseband. Then play it.
To your left shoulder. Take the winding path to reach the lake.
It doesn't sound like the voice originally, but you can still understand it though, right?
Yes.
So speech is not bad with an error in the carrier, and if it's not perfectly coherent. But in data, it's gone. You just can't get the data bits back. And in my phase lock loops class, that's kind of what one of the points of that class is, trying to get synchronization figured out so that you can get the bits back again. Because if you can't get a synchronous clock back again, you can't recover the data bits. You have to get the coherent carrier first, and then you have to get the bit sync working also. So you have two levels of synchronization that are required. If we now move on to amplitude modulation though, and here I will just use the speech file again, using a modulation index of 0.8. And if you notice what I'm doing here, I'm just taking 1 plus the modulation index. I've normalized the message to be of plus and minus 1 peak amplitude, and then I'm multiplying by the carrier. So now the carrier is filled because we've got, or pulled apart because we've got the bias term in there. Remember, in double sideband it was crossing through itself, but now it's open. And if we look at the spectrum, we see a spike right at the carrier frequency because we're putting pure carrier in. Now go ahead and demodulate it and envelope detect it. So rather than using a diode envelope detector, I'm using a software version of that, where I'm going to take the sign of the value and add 1 to it to make it look like a half-wave rectifier. So it looks like it's half-wave rectified. If I now come along with a low-pass filter, it cleans it up pretty good. There's some carrier leaking through based on the design of the filter. I think I have an improved filter. I've filtered it instead with a fifth-order Butterworth filter that cuts off at 1 kilohertz. I think that's what I'm doing here. Now the recovered message looks really good, and if I go ahead and listen to it, what do you notice that's different though?
Sounds muffled.
It's crisp. It's not as crisp because I've band limited it too much. If I was to open this up though, set that up to around 4 kilohertz.
Oh yeah, all the harmonics for the voice, all the tones. That comes back.
To your left shoulder.
Now it sounds crisper, right? Because speech needs about 4 kilohertz for audio. And this was an 8 kilosample per second file, and the folding frequency is at 4K, so that means the audio is 4 kilohertz bandwidth. So I think I had it cranked down there to 1 kilohertz for doing digital demod. Is probably why I did that, because I was checking out the digital. So if I was to amplitude modulate a digital bit stream, I would be able to get it back because I can envelope detect it. So now that I've got you interested in that, I should show you that. So now I'm going to turn the PN code back on for the AM modulation. There's the data bits, put it up on the carrier. And now you can see there is ringing in the signal, but with the amplitude modulation, the carrier never crosses, the envelope doesn't cross through 0, so we have a high level of carrier, then we have a close to 0 level of carrier, but it's not crossing through like it would be in double sideband. So we can recover these bits with the AM detector, and then we can implement the filter. The simple first order low pass filter doesn't do too bad, but now I'm going to go back to this guy and I'm going to set this back to 1000. The higher order filter, and there's the data bits. If I was to plot more time, I'd see more data bits, but it doesn't really sound any different, though. Listening to the data bits is not too exciting. But if I was to open the window up, you'd see more data bits. So that would be, I guess I don't have more. Let's see, I commented, uncommented. I'm just not plotting very many. I've got it limited in here. Take that up to 5,000. There we go. So I can recover the ones and zeros from that waveform, from amplitude modulation. But again, if I go back up here and look at the spectrum, there's my sync function spectrum that's been band limited, but you see that tall spike in there. What's that? Carrier. What's that doing? Sucking up power. If it's on Cheyenne Mountain or a big AM broadcast station, okay. If it's a satellite with limited power, we're kind of not being very efficient about things. You just wouldn't do that. SATCOM doesn't do that because it's looking for efficiency. More complexity though, but efficiency. But for the consumer, when AM came out, you had to use an envelope detector. So that kind of puts us in that position. So this right here is the example I'm going to go through, which is in the notes, just the Python version of it. So any questions on these demos? I'll do some single sideband stuff here, and then you're going to do a bunch of single sideband in the project one. You're going to be playing with it more. And you're going to be using all three speech vectors that I have downloaded from this website. You're going to have the US female, the US male, and the UK male. So you'll have three different distinct voices, and you'll be sending things over 3 channels, and you're going to be building a demodulator that can select, and you'll have to take into account some design considerations to make sure you don't. The signals are going to be packed right next to each other, and you'll have to do some filter design issues to make sure you only get one signal.
The circuits to Final Lab.
It might be. I don't know what that one is because I
It
didn't.
was more about channel noise, but we had to demodulate different frequency signals.
Okay. But this is going to be single sideband, and I'm willing to bet you didn't do single sideband.
I don't know the difference.
You don't know the difference?
Well, one's this way and then the other's that way.
Well, what we're going to be moving into here next is single sideband. So single sideband is not a new thing either, and it's reserved for special types of things. But when we jump into this, this is the idea. Double sideband had the upper and the lower. Single sideband, we've got the lower or the upper. So we can be more efficient. We can send twice as much information in a given bandwidth because we can pack channels closer together. Again, it's old. I won't say it's retarded. It's just not the thing that is used that much anymore. But I'm really interested in the philosophical reason that why comm people get so wrapped up about stuff. They want to do things that are efficient and effective to solve a problem. You just don't want to go waste things like, you know, if everybody wasted everything, then we'd have nothing to share. We'd have very limited resources and we'd be fighting over it. So we try to do designs that are robust and give something for everybody. But yeah, the world's not perfect. We got candidates that are in the primaries today that have very differing points of view, and I don't know where we're headed right now, but I do know that 5G is supposed to give us more bandwidth, but it's more expensive and a lot of resources are going to be spent on it. Do we need it, I guess, is what I'll say.
Not with Starlink, we don't.
What is Starlink?
It's the internet service that Musk is putting up in low Earth orbit.
Oh, okay.
Supposed to drop in America?
End of this year.
So it's
I'm just sick of Comcast. I'm just sick of
It's-
CenturyLink.
it's another go at Iridium then, is what it amounts to.
Comcast is the only guys who get us $250. Like, they're the only guys, and they charge $50 for it.
See, there's still limited resources. Motorola. I worked for Motorola down in Scottsdale, Arizona, and I did some work on the Iridium project, and I had friends that worked on it. It became so expensive, Motorola couldn't afford it. They kind of defaulted on it, and it's still a set of satellites that are up there. It's called Iridium. Does anybody know why it was called Iridium?
Is that thing from
Supposed to light up the world.
No, I mean, I'm not a chemist, but we don't have a periodic table in here. I think it's element 77 is iridium, and that's how many satellites are in the constellation. Check that out.
Well, that's
I think
not
that's,
enough for SATCOM or for global internet coverage.
well, it was what was affordable. Launching 77 satellites was still a pretty expensive proposition.
Musk is putting 66 or 60 in a shot. He's already got 240 up there.
Okay. Well, we'll see. I'll be a skeptic.
It's all right. You can build telescopes in space too.
Only,
That'd be nice.
as a backpacking type person who was involved with high adventure and Boy Scout type stuff, yeah, it would have been nice maybe to have that ability to communicate. But when you go into the backcountry, it's okay by me to just sort of be gone and not have any communication with anybody.
Yeah, my dad's the same way.
What?
My dad's the same way.
Escape it?
Yeah, he's not afraid to just throw his phone into the water. Said his job will get him doing
Yeah, it's added weight. I don't want to have that weight when I'm backpacking. I'd rather have it in something to stay warm or some food. Or, I mean, it's all trade-offs there too. If I go to the Boundary Waters like I did a year and a half ago, and you plan to go fishing, then maybe you're going to catch your food. But you can't always count on the fish biting either, so you might do that another way.
Colorado?
What's that?
I thought there was a catch limit in Colorado, or like keep limit.
Depends on the.
I don't know. I've been up like
The
in
only one you can catch in Colorado is crab.
the brook trout, you mean, or the cutthroat and that stuff.
Yeah.
Yeah, I've definitely had those up at high elevation.
That wasn't. That's everything. There's no lot in Colorado.
Okay, the next example I want to do, though, is one that involves a little bit more calculations. This one is kind of like the homework problem that you turned in. This is just single tone modulation, and you just walk through using the definitions that are in the blue box here. And then if you have to work like problem 311, I think the development just above that was also useful, right? You came to see me, I used that to help get you going on that
Now
problem.
We're actually doing it.
What's that?
Now we're doing it.
Well, now I'm just kind of reviewing how you can solve problems.
Yeah.
Yeah, I put you into a bind where you had to be resourceful and try to make headway on your own. But the examples are in here. So this example just takes you on through the basic single sinusoid case, which it just boils down to the standard equation. And I got it into this form to get the total power. And the only thing that's left really to get the total power here is to just say that that is going to be 1/2, because when you have a single sinusoid, the power in that single sinusoid, when it's been normalized to be the normalized form of the modulation, is just 1/2, or 1/2. And then the rest of this plugs in to the way this equation was set up, or the way the problem was set up. So in this problem, you were given a total power of 1,000 watts. So you said that the power in the carrier plus the power in the sidebands have to equal 1,000. But then when you make these substitutions into there and put in what the modulation index was given, then you can backwards solve for how the power distributes between the carrier and the sidebands. And so it ends up being this algebraic result. I could give you variation on this for the quiz problem. You know, this is definitely a candidate problem for the quiz. So, any questions on it? What would be the variation that I could give?
Multiple sine waves.
Well, that's the next problem. I'm not going to do that on the quiz because that's too hard. I want to take you through that to realize that it gets more complicated in a hurry unless you have a special scenario, which I've been known to do in a quiz before, so I guess I need to point that out to you, see how I can make it be more obvious. But the variation I could do is I could not say the total power is 1,000 watts. I could just simply say, you know, I could just plug a number into here and say this is 500, and then say the modulation index A is equal to 0.8. And then once you do that, then you would just be able to walk right into this instead of having,
Powers.
you would just have 500 squared in there, 500 squared in there, and then this would be 0.8 squared. And the normalized message brings in a average power of 1/2, so you'd just be able to plug the numbers in and calculate away. That could very easily be what the quiz could be. But what's yet another variation? I mean, I'm just giving you some ideas of possibilities. Another thing could be we're going after efficiency, so we might decide to make efficiency be a parameter. What does A have to be to get the efficiency to a particular level? And right now, if you just use this formula right here, if you kind of look at this one, suppose I wanted to get the efficiency to 40%, how could I go about I could say what modulation index would be needed for the case of a single sinusoid to get 40%. Does that sound like a reasonable question to ask, or a question to ask? Or what's the maximum efficiency I could get with a single sinusoid? That'd be another question to ask, right? What would be the maximum efficiency? In other words, the ratio of power in sidebands divided by the total power. How could I maximize that number? Well, what's the first thing I would do? I would set the modulation index to what?
0.
Actually 1, right? Because 1 is going to make it, the modulation, 1 is going to make the, this thing just touch. Right? That's what 1 would give you. It would just be touching right in there. It's 100% modulation. So I could set that equal to 1, and then I could go up to the side here and say, so 1 times mn squared of t, the average value of that, over 1 plus 1 times mn squared of t. If it's a single sinusoid, you know that the power in the normalized message is what? If you have just cosine omega mt, the average power of that is just the amplitude squared divided by 1/2, right? So that'd be 1/2. So I could put those numbers into here, and I'd have 1 times 1/2 over 1 plus 1/2 and then I would have 1/3. Is that right? 33%? Did I do that right? So if I was to say find A to get an efficiency of 0.4 for a single sinusoid, you'd have to tell me can't do it. I turn the modulation index up to 1. I can't get any higher than 0.33. You might be able to pick a different type of waveform, and that's what I did in another example in here. I picked a pulse train.
Would we be allowed to just add those equations onto our cheat sheet? Just try to memorize them?
For the quiz, I'll say no, because I'm going to make you focus on it, because I'm giving you very specific quiz requirements. But for the exam, yes. They will go on your two-sided sheet that you'll be preparing for the exam. That sound good? And the quiz is Thursday. Exam's a week from Thursday, so I'm just trying to have you put the focus on, and then I think you can do it for that, because it's just not a big deal. Too much stuff, then your brain gets scrambled. So here I did a pulse train example, and so for this pulse train example, with A equaling 1, I was able to starting to have problems here. I'm waiting for this pen to die so I can put my new battery in. There, it came back again though. So I set A equal to the maximum value and I got 67%. But a pulse train is kind of an oddballish signal for AM modulation, but it's an example of how, with a particular duty cycle in this case, the duty cycle was 1/3, so it was on for 1/3 of the time and low for the other third of the time, but then I balanced it so the average value was equal to 0. That gives me that strange number, but otherwise it's not going to be that high. So I'm ready to go work this multiple sinusoid problem just so you can see how that works out and get a better flavor for how a more complex signal would be. And I guess I did have a note in this problem. If you go with a 50% duty cycle square wave, then the maximum efficiency is just 50%. And then here's the example for the single sinusoid case, I think. Okay, multiple sinusoids. So suppose you have a bunch of tones in the message, which could be a model for a speech or something, just saying let's put a bunch of tones up, giving them different amplitudes, and say this is synthetic representation of speech. So in this case, I don't know how to get the normalized message unless I can actually plot the function. I can't look at this and say what is the most negative value of that waveform. Remember, that's how the normalized message is formed. You plot the waveform and then you normalize by the most negative value that the waveform takes on. We can always overbound it though. We can say worst case scenario, we want to find the minimum value of m of t, but we can overbound it. We can find a lower bound by saying, let's just suppose there's a particular time where all the sinusoids combine constructively, so you just get the sum of the amplitudes. And in fact, that case is going to happen pretty readily, and this is the trick. So Colton, you were looking at me, and I was looking at you when I said that there's a trick. Suppose all the cosines have 0 phase. Then I can just say what's the most negative value that sum of cosines will have. I'll just set t equal to 0, and that will give me the maximum value, but then I can use that as my bound for the most negative value, which may or may not be true depending upon the phasing. So I guess if I had pi in here, that's what would do it. if that was pi and I set t is equal to 0, then I'd have all the cosines would have a value of minus ak, and I'd just be adding all those ak's up. But in general, it's more complicated. So a problem in the book is to consider 3 tones, 65, 100, and 35. They're given some amplitude values, they're given some phase values. So what I did in this example was done in MATLAB, so it's old MATLAB code. But what I did over here is I did the same thing over here in Python. So I had a sum of multiple sinusoids, and I actually wrote a function that would take any number of sinusoids, and you just have to feed in lists of frequencies, phases, and amplitudes, and then this function returns that minimum value, or it allows you to plot the multiple sinusoids, and then you can find the minimum value. So that's what I did here. And the numbers that you see in here, this is from that example problem right here. So I set a sampling rate, or the number of samples. I said generate 1,000 samples, and there it is. So actually this tells you something when you just pick frequencies kind of at random that aren't necessarily harmonically related. What do you see about this? The peak value and the most negative value are not equal. So you got to be careful there, because see, this looks like it's hitting 8, where this is hitting not quite minus 8. So the lower bound, if I just added all the amplitudes up and took the negative of it, would be 9.7. But when I actually do the numerical solution, I get minus 7.24. So you would be over-normalizing in this problem. So then the next problem in working this is, once you know what that minimum value is, then you have to normalize your message by that minimum value, and then use that to set up your normalized message. And then once you have the normalized message, then you want to get the average power in that. And the cool thing about this is we work through this in chapter 2. If you have sinusoids at distinct frequencies, the powers in the sinusoids, the power in the sum of those sinusoids is just going to be the sum of the powers. Remember that little development? Somebody asked me about that when I had that in there. It's in the Jupyter Notebook, a proof of it. So in order to get the average power, I just take the amplitude squared over 2 for each of the original sinusoids, and then I take into account what the normalization factor was to convert it into a normalized message, square that. So I end up with the power in the normalized message is 0.3227, and then assume the modulation index. So here I'm assuming A is equal to 1 again, and put that in the efficiency equation, and I get 0.244, so not very good. 75% of the power is in the carrier, not in the information carrying sidebands. But you can argue something. What would you do if somebody wanted to argue about this? The power, only 25% of the power is in the sidebands, and your argument might be, but if the alternative would be to use coherent demodulation, I would have to spend more money on my receiver and make it be more sophisticated, and that's going to cost more money. It's going to use more battery power and more energy. So is it more efficient to just have the transmitter put up that extra power for the carrier so that the receivers are less expensive and use less energy? I don't know what the answer is. Obviously, the answer depends on, to some extent, on how many people are listening, right? If there's only one person listening, they should have the expensive receiver and not require the transmitter to do all that power waste. right?
Yeah, that makes sense.
So when I was on a study project at Emergent a number of years ago, we were looking at something for the Air Force Satellite Control Network. We were looking at bandwidth efficient modulation schemes for AFSCN, and we were just looking at ways of designing waveforms that would allow for more spectral efficiency, with the thought being that the government would sell more spectrum off to public use. I mean, interesting thing is, if we didn't use all the spectrum, could the government make enough money by selling spectrum that it doesn't absolutely have to use anymore to the general public for consumer use, and would that significantly reduce the national debt? It's an interesting idea, I think. I didn't go through any numbers, but we'd figure out another way to spend money in the government and we'd still have the same debt. It's crazy, right? I don't know what you guys think about it. Brings me back to the elections that are going on right now. It's like everybody wants to get us more, but yet nobody thinks about the debt and what does that mean. But this is not political science class, so I'm not going to go into a debate on that, but it's just interesting. Right?
Yeah.
You can die with debt, and that won't hurt you as you die, but it might hurt your family members that have to figure out how to get things taken care of with your creditors and bankruptcy. And
No, you don't have any more debt.
yeah, you don't have any more debt because you don't even care about it anymore, but you're talking about your family?
No, I mean, they can go after your family if you
Yeah,
own
that
debt.
dies with you.
Yeah.
It's illegal.
Okay, I forgot about that fact. At any rate, it just makes me think about some crazy things.
Oh, that's the case. So what is the most efficient and the least efficient modulations?
Single sideband is pretty efficient, but there's other types of phase-coded modulation for digital that my dissertation was on that, and they were very efficient. In a digital modulation scheme, and we'll talk more about this later, they talk about bits per second per hertz of bandwidth. That's the unit of measure. So it's how many bits per second per hertz of bandwidth that you can do. But then you have trade-offs involved with that. So there's limits on that. And Shannon, who did coding theory and stuff, comes up with Shannon's bound for, reliable communications over a band-limited channel. But the problem is his theory doesn't tell you what the code is that you're supposed to use. It just says there exists a code, but finding it is not, explained. And then billing the decoder that's reasonable is not necessarily easy to do either. So that maybe isn't the place to go looking, I don't know. But there are some beautiful theories out there. Just like in pure mathematics, there's some beautiful theories that don't really help us solve real world problems because they're not that practical. So here I just did the calculation of the spectrum in that case, all the spectral lines that are above and below. So when I just wrote it out mathematically, and then in this case I had MATLAB plot the picture. In the notebook it's done in Python, but oops. So obviously this is on a linear scale, but you see a lot of power on the carrier, and then the sidebands are tiny next to that. I think I probably did the same thing over here. Yeah, I have a example of plotting the spectrum for multitone AM, and I actually, once you know it, I wrote a function for doing that. I like doing that because that's called code reuse. If you can write it once, you get to use it again. And I'm doing that in my phase lock loops project I've been trying to get, or problem I've been trying to get out to that class. I've written some helper functions so that their work is easier. And your project has helper functions that go along with it too. So I give you helpers I give you a notebook that has examples in it. So let's go on to single sideband. So you can work the homework problem. So we already looked a little bit at this. Double sideband had an upper sideband and a lower sideband. The spectra are related, has even symmetry. Phase spectrum is odd symmetric. So the bottom line is what this is telling us is that information is redundant, so MOT can be reconstructed from one or the other of the sidebands. So transmitting just, upper sideband or lower sideband is what single sideband is all about. So when we have a single sideband signal, we still have the carrier frequency located either at one side or the other, because that's the way it's created. But if it's upper sideband, the carrier is going to be on the lower side of the single-sided spectrum, and if it's lower single sideband, it's on the upper side. And if you were interested in amateur radio, this is the type of thing that amateur radio people love to do, use single sideband. And for better or for worse, I got interested and introduced to it at a very young age because my father was really good about telling us what he was doing, since when he was talking on his high frequency radio setups with the big tower that he had on the roof of the house, or on a tower that you could climb and that was way above the house. If we were watching TV, our TV was all messed up because we heard him talking on the radio. If we were listening to the stereo, it managed to make it into the stereo. It was like, my mother generally wasn't all that happy about it, but he'd always say, I'm going to be on the radio a certain time talking with other people, and forget about certain things in the house, because the radio, his transmissions was kind of messing things up. And that was before the day of the microwave oven. So, I mean, microwave oven came along and that can mess up your Wi-Fi, right? It does in my house. It doesn't totally wipe it out, but it definitely takes the throughput way down. So the best way of understanding how to form a single sideband signal is with the aid of the Hilbert transform. So we're going to jump back over to chapter 2 and look at the Hilbert transform. So the Hilbert transform is named after mathematician, physicist Hilbert, and it sounds sophisticated because it's like, oh, I know Fourier transforms, Fourier series, Laplace transforms, Z transforms, and now I'm going to learn about the Hilbert transform. You're thinking, this is going to be just another one of these transforms, but actually it's not as big a deal. But it is called the Hilbert transform. So the Hilbert transform, very simply, is what is right here. In the frequency domain, it's a filter that has a minus j in front of it, and its function of frequency is SGN, which called the signum function. But we're doing work with it in Python or MATLAB, it's going to be the SIGN function. That's the way it's defined. So quickly jump over here to a convenient spot. I guess I'll just add a cell in underneath here. Just type it in, SIG, hit tab. Does it have anything? There it is. Then put parentheses and then do shift tab. And it tells you what it does. It doesn't tell you that it's signum by name, but it says it's the sign function, returns a -1 if its argument is less than 0, a +1 if the argument is greater than 0, and 0 if the input is equal to 0. In the case of the definition over here, it's the same thing. So it's conveniently defined in our tools. And we can go ahead and use it in a time domain expression. So if we want to find what the Hilbert transform of a signal is. In other words, we want to get the Hilbert transform of x of t. The notation for that is going to be put the hat, or circumflex is the official name for that symbol, over the signal whose Hilbert transform we want to find. That would be the inverse Fourier transform, using the convolution theorem now, saying we'll take the Fourier transform of x of t and multiply it by minus j signum of f, and then inverse Fourier transform that product, and that would give us the Hilbert transform. We might want to consider doing it in the time domain, so in which case then we'd want to get the inverse Fourier transform of the Hilbert transforming filter itself, h of f. And getting after that takes a little bit of finagling, and it's talked about here. You use the duality theorem and the differentiation theorem to get there. I don't really want to spend any time on it because it's kind of messy, and in the end, here's what it is. It's that. And if you go to put it in an integral, namely a convolution integral, to actually convolve with that impulse response, you get these integrals. And what's your first reaction when you look at that integral? Do you feel at ease, or do you feel like, what?
Yeah, more like,
My reaction is I see that lambda in the denominator, and I say, this is a singularity, and I'm going to have to be very careful as to how I even can do this integral. So I don't find this to be particularly practical, but we are going to have digital filters that can do the Hilbert transform, and I'll discuss how the design capabilities of SciPy.signal and MATLAB's signal package can do Hilbert filter design. So we get an impulse response for a digital filter that is workable. But in the continuous time domain, this is just kind of an ugly thing to have to work with. Instead, we prefer to do most of our thinking in terms of the frequency domain. So for example, the Hilbert transform phase shifts the signal at all frequencies by minus pi over 2 because of that minus j that's in the frequency domain. And from that, we can reason out that if we were to Hilbert transform the Hilbert transform, we'd be phase shifting by minus pi over 2 a second time, and that would be double the angle, so that'd be minus pi, and that means we're going to get the signal back again with a minus sign in front of it. That makes sense, doesn't it? Shifted by minus 90, send it through the Hilbert transform filter a second time, be minus 180, and that's just inverting the signal. And we can get at that very simply in the frequency domain by just taking and multiplying it out. Minus j signum of f quantity squared, so we'll end up with the signum function squared is just going to be 1, except that f is equal to 0, which is just an isolated point. And then minus j times minus j is going to be what? J times j is minus 1, right? And minus times minus is plus 1. So a good example is if we have a cosine wave and we shift it by Hilbert transforming it, we should get what? We're going to shift it by 90 degrees. We're going to get sine. So the Hilbert transform of cosine is sine, and it's worked out here in the frequency domain. So we're avoiding that convolution. We're just multiplying through by the frequency response of the Hilbert transforming filter. And now I'm in trouble. No, I'm not in trouble. Never mind. The homework you're going to do for next Tuesday involves this. We're still good for the quiz on Thursday because we're out of time right now. There's nice properties of the Hilbert transform, which we'll be talking about next time. And then there's this other kind of cool thing called the analytic signal, where we form a complex signal using x and jx hat. And then we talk about complex envelope and other things that kind of get kind of interesting. And this is where I came up with an idea for one of the design teams, the ISAR team, which really only Chris knows of the ISAR team, right? You don't know that much about their project, though, probably.
No, I haven't seen much of their presentations, to be honest with you.
Okay. Well, I'm coaching them.
Yeah, I heard that theirs is a near impossible task
I don't know if it's
for
in.
their budget
Oh, well,
and their resources.
it's a science experiment, so they're just doing a bunch of experiments and taking measurements in the anechoic chamber and then out in another anechoic chamber at CEI.
Yeah, see, we're actually putting in a product.
And likewise, the Harris team that I'm working with, they're delivering a product also.
Are they?
Yeah.
Oh, that's right, that's the little box they gotta make.
Well, they're doing it in Raspberry Pi. So I'm done for right now, though, and we'll pick this up again. Does anybody have any questions?
Not to pertain to this, I do have a question for you though.
Okay. You want to go up to my office?
No, it'll be a brief one.
Okay. So everybody remember the game plan? There will be a quiz, and then I'll put out the solutions that relate to the problems down to the, excluding the last two, because the last two you're going to turn in next Tuesday. So I think I think the roadmap is pretty reasonable to get to the first exam. I wish everything that I was working on could be this easy. I mean, I'm not saying this is easy. It's just we start the first interviews for the power systems professor on Thursday.
Someone squeeze
Are you
on the
getting a new
problems
power
at
systems
once.
professor?
Yeah.
We're going to have a full-time tenure track faculty member in that area.
Okay.
We're not going to have somebody that only comes in
Heard from what I
on evenings. We're going to have a real person do it. So
Excellent.
double side bearing.
Steve is on the committee, though. I recruited him.